Hi, I'm Kenji and welcome to my video on my final year project, which is complex motion synthesis using diffusion models. It sounds like a complicated project name, but here's what I'm actually doing. So, diffusion models. We've definitely heard a lot about them in the past year. There's image generation with stable diffusion, and now even video generation with Sora. But there is motion generation too. Well, it turns out that if you treat motion capture data just like an image, you can actually generate them too, resulting in motion. And we're going to call these models motion diffusion models. And for my project, I've managed to do three different things with these models. The first is that I've built a pipeline that integrates these diffusion models into the Mujoko environment, which is a physics simulator. I've also explored different diffusion model architectures that support motion generation and adapted them into my pipeline. And finally, I've performed an analysis of my best performing diffusion model to synthesize new motion. So why are we even doing this? Well, motion generation is very useful for animation and games. We already have humanoid agents using these technologies that can transition between various movements very smoothly. And a lot of research has already been done with using diffusion models for generating motion. But they all have one major issue, which is that they don't really incorporate physics into the motion generation process, resulting in sometimes unrealistic motions. And if we want to one day combine these generated motions onto a robot, we need to at least test them out in a physics simulator like Isaac Sim or Mujoko. Before we move on, let me give a quick refresher on how diffusion models work. So diffusion models have a forward diffusion process and a reverse diffusion process. In the forward diffusion process, we iteratively add noise onto our training data for a number of time steps until it becomes unrecognizable. And the goal of the diffusion model here is to learn how to undo the noise added at each time step. In other words, it tries to predict the amount of noise that was added onto a noisy image given its time step. And once we have a model that knows how to undo the noise at each time step, we can start the reverse diffusion process with pure noise as our input. And the process will iteratively remove the noise until we have a clear image. And this is essentially what our pipeline is doing as well. The purpose of this pipeline now is to use a diffusion model to learn from a single motion capture data, and then reconstruct it as a reverse diffusion process. And the reason we want this is because new motion can be easily synthesized in this form. Here, the red path represents training and the blue path represents the generating process. We first start off the training process by extracting the joint features from our frames. In our case, we use joint positions and joint velocities, and then we can apply them into a diffusion process and have the model learn to predict the noise added at each time step. And once we have that, we can start generating motion. In the sampling process, we first start off with some random joint positions and velocities, and the model can iteratively denoise them, resulting in generated joint positions and velocities, which we can then render in Mujoko, completing the pipeline. One thing I forgot to mention about here is the conditioning function you can see here in the loop. Basically, this is a function that lets us set certain constraints to the noisy data at each time step before feeding it back into the diffusion model to denoise. This is just a means of conditioning the generation. Also, the diffusion model component here can essentially be replaced with any other diffusion model architectures. So previously I mentioned that we can just replace the image data with joint data and it should work out fine, right? Well, except it doesn't. You see, turns out with motion data, we introduce another dimension to consider, which is time. So we need another architecture, one that can support temporal data. One promising architecture I found was MDM, which is a text-to-motion model. What's special about its architecture is that it's transformers-based instead of the common UNet architecture. And it's using transformers because they are better for capturing temporal data, which is what we need for motion. It also introduces the idea of using geometric losses, which means that instead of just calculating the loss purely on the frame data, we should also extract physical motion features like joint positions and joint velocities and include them within our loss calculations as well, resulting in a much more balanced loss calculation. After some tweaking and adapting to fit the MDM model into the pipeline, I've managed to train the model on this spin kick motion, and here are the best results I could get. Yeah, the motion doesn't look smooth at all. It has some poses, right? But it looks like it's skipping some frames, and it's spinning around back and forth in the wrong order sometimes. But don't worry, we have a backup architecture, so let's take a look at that instead. The next promising architecture to look at is the diffuser model. It's an interesting diffusion model that was used for planning in reinforcement learning problems. The model was essentially trained on pairs of states and actions for a given task, and it learned how to generate a plan to solve the problem. In terms of its architecture, it uses a temporal unit with a local receptive field so that for each state and action it has to generate, it takes a window of nearby states and actions into consideration as well, achieving local temporal consistency. And after many diffusion time steps, the local temporal consistency will develop into a global one. The interesting idea here is that if we squint our eyes a little and treat the joint positions as states and joint velocities as actions, we could technically phrase our motion generation problem into a reinforcement learning problem. We adapted this idea and trained the model on the same spin kick motion as before, and here is the results. And there you have it, we have smooth motion. Don't worry if you can't tell them apart, we did a survey with people and no one could tell them apart as well. Now that we have a model that can generate smooth motions, we can try using it to generate new motions. And here are 3 methods that I would like to showcase to generate new motions. The first is long motion generation. One interesting property of the diffusers model is that it can do variable length planning, meaning that it can generate longer or shorter plans depending on the size of the input. In the context of motion, this means that we can also use it to generate a longer motion if we give it a longer sequence of frames to denoise. To test this out, I've extended the number of frames of the input to 3 times its original size, and here is what it generated. It looks like it's just doing random flips in between, but we can actually specify when to flip using the next method, which is motion in-betweening. What it essentially does is that it fills in the gaps of a provided motion. Here, I am using the conditioning function to inject the upside down pose into specific keyframes of the same input sequence as before, and in-betweening will generate the gray sections. Now, it is able to do the flips at specified times. And finally, we have motion editing, where we can hardcode some joint values to generate new motion. I have a cut wheel over here again, and by setting the conditioning function to restrict the motion of the arms, it generated this. And yeah, that sums up my project showcase. I've built a pipeline for diffusion models in Mijoko, adapted some architectures, and tested them out on synthesizing new motion. The current implementation is still quite limited, but I'm sure there's a lot of potential for the future. Thanks for tuning in.